All right. So today we're happy to have Monica Pate here from Harvard to tell us about soft factorization in gravity. So thank you very much, and please take it away.
Okay, thank you for the invitation to speak at your seminar series this afternoon. The general purpose of my talk today will be to explain how symmetry can be seen as the origin of a variety of universal infrared behaviors of scattering amplitudes. And so in particular today, I'll be focusing on the results of this paper I wrote last May with several collaborators, Mina Himwich, Shruti Narayanan, Nishar Gopal, and Andy Strominger. In this paper, we explain how this general paradigm of symmetry being the origin of universal behavior in the infrared applies to soft factorization of gravitational scattering amplitudes. So a general motivation for this work is really to attain a deeper understanding of universal phenomena. And so therefore, a natural place to start is to consider under what general circumstances do we expect a notion of universality to emerge. So one context in which we often expect to find universal behavior is in the infrared sector of theories. And so the intuition there is that non-universal details appear at short distances, and so low energy probes are insensitive to these microscopic details. Now, another context in which one might expect to find universal phenomena is in the presence of a symmetry. And so in this case, the idea is that symmetries protect observables from depending on non-universal specifics of the system. And so then the next thing that you might wonder is whether the two are related. And now, in general, there's no general principle why they need to be, but in some cases they are. And so a very hand-wavy schematic argument about why you might think they could be related is suppose you consider the conserved charge for, say, a continuous symmetry. Well, then you can write it as the spatial integral of the zero component of the Noether current, which, if you interpret it as a Fourier transform, is picking out the long wavelength behavior of the current density. So in other words, this conserved charge is telling you something about long wavelength data. But today we're going to do much better. And so in particular, what I'm going to be describing to you is examples of precise relationships between symmetries and universal infrared phenomena in the context of gravitational scattering amplitudes. So the outline for my talk is in the first part, I'm going to review one instance of this precise relationship, which is the equivalence between Weinberg's soft graviton theorem and a Ward identity for infinite dimensional asymptotic symmetries known as supertranslations. And this suggests that perhaps more generally, the universal structure of infrared singularities of scattering amplitudes might be understood as arising from symmetry. And so the second part of the talk will explain how this does indeed apply to the universal soft-hard factorization of gravitational scattering amplitudes. And in the final part of the talk, we'll see that the soft part of the S matrix can be used to construct a natural infrared safe observable, which I'll then explain can be identified as the universal observable known as gravitational memory. Okay, so since the first part of this talk will be to explain the equivalence between Weinberg's soft graviton theorem and a statement of symmetry of the scattering problem, I find it useful to give a more abstract, begin with a more abstract discussion of what symmetries mean in the context of a scattering problem. So generally, we can think of symmetries as transformations that preserve the laws of physics. So in other words, they leave the dynamics invariant. And in particular, this means that they map solutions to solutions. And so in this sense, symmetries are useful because if we have a set of solutions, we can obtain new ones by acting with the symmetry. So then the scattering problem is the answer to the question, given an initial state at some very early time, what is the final state at some very late time? And so in this context, solutions take the form of pairs of initial and final states that are related by time evolution. So if we put these two ideas together, then we find that symmetries in the context of a scattering problem are transformations of initial and final state pairs that preserve time evolution. So to reiterate, if we have an initial and final state pair that are related by time evolution and we act with a symmetry, then we obtain a new pair of initial and final states that are still related by time evolution. Okay, so now we'd like to understand how Weinberg's soft graviton theorem can be interpreted as a statement of symmetry of the scattering problem. And so the first thing is just to review what Weinberg's soft graviton theorem is. So what it is it's a statement about scattering amplitudes that involve the emission of a soft graviton. And what the theorem says is that in the limit, as the energy of that graviton is taken to zero, the scattering amplitude develops a pole in that energy with a universal residue. So here we're going to find it useful to parameterize graviton momenta in terms of an energy and a unit vector, which we can think of as specifying a point on the two-dimensional sphere. So then on the left-hand side here, we have a scattering amplitude in which a graviton is emitted. And in the limit, as its energy is taken to zero, the scattering amplitude develops a pole. And so this object here picks out the residue of the pole. And what the soft graviton theorem says is that residue is universal and given by the scattering amplitude without that soft graviton multiplied by a universal number, which is known as the soft factor. And so this soft factor depends on the direction in which the soft graviton was pointing or is propagating, the polarization of the soft graviton, and the momenta of the other particles, the other hard particles that are participating in the scattering process. So as I said, in the motivation, the general idea is to understand the relationship between universality in the infrared and in universality due to symmetry. And so that's just to say that Weinberg's soft graviton theorem is usually thought of as a statement of universality in the infrared. And the reason for that is simply that it's a statement about scattering amplitudes that involve a low energy graviton that is only probing long distance properties of the scattering process. And so the aspects of universality that are observed is that this soft vector only depends on the momentum of the external particles. It has the same contribution for each external particle, and it's really independent of the precise theory. So for example, it can't tell the difference between whether this is a theory of fermions or whether the other particles in the scattering process carry other conserved charges. And that's simply because the soft factor only depends on the momenta of the external particles, but none of their other quantum numbers. And finally, the soft graviton theorem is an exact relationship between scattering amplitudes, which could in principle be quite complicated. So if we recall actually the discussion of symmetries in the context of the scattering problem, the abstract discussion from the previous slide, the fact that this is an exact relationship between scattering amplitudes actually hints that it might be the result of a symmetry. So previously we saw that the symmetries map pairs of initial and final states. And so such an exact relationship might be interpreted as one of these mappings. So indeed, that's true. And there's actually a very systematic procedure in which you can turn soft theorems into statements that the S matrix is invariant under infinite dimensional symmetries. And so I'm now going to review what that procedure is. So the first step is that we can regard the soft factor Sk as the eigenvalue of a single particle state under some operator, which we're going to call QH, which depends on the direction towards which the soft graviton is propagating. And we're going to interpret this as implementing a transformation, delta, on this single particle state. And so thus, we can view the right-hand side of the soft graviton theorem as giving the net transformation of single particle states that comprise the asymptotic state asymptotic state under this transformation delta theta phi. So then what this soft theorem is saying is it's the statement that the S matrix is invariant under the transformation delta theta phi of single particle states, provided that we add a soft particle. So with that interpretation in mind, let us introduce a second operator, which we're going to call QS, whose job in life is simply to add soft particles to the asymptotic state. So by doing this, we can represent the left-hand side we can write it in a similar way as the right-hand side. And by moving both to one side, we find that the soft theorem can be written in this form, and therefore can be interpreted as a statement of invariance of a symmetry generated by a charge Q, which is given by the sum of this QH and QS.
Can you clarify, do you mean that you add a literally zero energy particle when you say soft?
Yes, this is a literally zero energy particle.
To what extent do we usually include literal zero energy particles in the Hilbert space? That is not something I'm typically familiar with doing.
So typically one doesn't, and so it's something that I'm not actually going to explain in this talk, but the fact that one doesn't is actually can be understood as the origin of infrared divergences in scattering amplitudes. And so if you actually include a degeneracy of vacua that include these zero energy particles, you can construct scattering amplitudes which are infrared finite. So just to reiterate, this is not what is standardly done, but I would advocate it is what one should do. Did you want to say something more, or?
No, I think it would take us on too long of a digression.
Okay. Okay. Right. And so in particular,
Can I ask another question too? Sorry. So you showed us that soft gravitons imply this symmetry. Is something like the converse true, that this symmetry implies gravitons?
So you can begin by constructing charges so I haven't actually told you, this symmetry was already known, and there's a physical interpretation for the symmetry, which I have not told you yet. But you could begin with the charges which you know generate that symmetry, and then derive the soft theorem, if that answers your question.
So gravitons are the only way to kind of satisfy the constraints you're getting from that symmetry? Or could you imagine different, a different?
Yes, sorry, this is a symmetry in a theory of gravity, yes.
I think what Luca is asking is, are there other representations of this symmetry algebra other than on a Fock space of zero energy states? That's just a question about the representation theory of some part of the BMS group.
Yeah, I don't know. That's a good question. Right. So the last thing I wanted to point out was that these charges were parameterized by the point on the sphere towards which the soft graviton was propagating. And since a graviton can propagate in any direction, we get one charge for every direction in which soft graviton can propagate. And so there's an infinite number of charges, in other words, an infinite number of symmetries. So this is the sense in which we can always interpret soft theorems as statements of invariance of the S matrix under an infinite dimensional symmetry. So I just gave a sort of formal argument about why the Weinberg soft graviton theorem could be interpreted as a statement of a symmetry, but in order to actually identify the physical interpretation of the symmetry, it's helpful to parameterize these transformations by functions on the sphere as opposed to points. And so to do this in a nice way, the first thing to notice, let's first consider the case when we're studying scattering that only involves massless particles. And so in that case, we can take all particles are null, and we can parameterize every particle by an energy and a direction in which it's propagating. And then what one finds is that the soft factor for external particles that are massless is in fact a Green's function on the two-dimensional sphere. So that just means that there exists some differential operator, which when you act on the soft factor, you find a delta function that has support when the momentum of the soft graviton and the momentum of the massless particle are aligned. And in particular, also, since this soft factor is proportional to the energy of the external massive particles, that's why one finds some factor of energy here. So using this, we can now construct charges that act locally on massive external particles. And so what I mean by that is if we take these charges, which were originally parameterized by the direction in which gravitons are propagating, and we act with this differential operator and we convolute it against an arbitrary function f, then we obtain a new set of charges, and their actions on massless asymptotic states can be deduced from the original ones. So in particular, if we want to determine the action of such a charge on a massless external particle, well, it was given by the hard part of the charge, but now this hard part of the charge can be obtained from, or the action of this hard part of the charge can be obtained from the one parameterized by points by simply acting with this derivative operator, which localizes this to a delta function and integrating against some function f. So that's just to say that if we just decided to parameterize our infinite number of symmetries in a slightly different way, and their actions on massless single particle states return the energy and the function, an arbitrary function evaluated at the point towards which that massless particle is propagating. Okay, so we've just identified a slightly different transformation as following from the soft theorem, but this is nice because it has a nice physical interpretation. So in particular, let's consider the case when this function f is just a constant and equal to 1. So in that case, we find that the transformation of a single particle state just returns its energy. But we know that the transformation of a momentum eigenstate that returns its energy is an ordinary time translation. So we can identify that symmetry as just being an ordinary time translation. Now, on the other hand, if f is an arbitrary function on the sphere, well, then we find the energy multiplied by that function evaluated at the point towards which that massless particle is propagating. So we can think of f as parameterizing the amount of translation at every angle. And since f is an arbitrary function, this means that there is an independent time translational symmetry at every angle. So thus, we found that Weinberg's soft graviton theorem implies that scattering is invariant under angle-dependent time translations. And these were known previously from the general relativity literature, and they're called supertranslations, and were discovered by BMS, so Bondi, Vandenberg, Metzner, and Sachs. So in order to understand the physical interpretation of the symmetry implied by Weinberg's soft graviton theorem, we focused on the case in which external particles were massless. But nevertheless, the story has a nice generalization to massive particles in the external state as well. So to understand that, the first thing is that the original argument I presented applies where we were parameterizing the symmetries by the points on the sphere towards which the soft graviton was propagating. That applies just as well to massive particles. So in particular, in that case, we really could interpret the symmetry transformation of massive particles as we could interpret them as being eigenstates of the hard charge where their eigenvalue is the soft factor. Now the difference comes when we parameterize our symmetries in terms of functions f. So there, we just follow our nose, and in order to deduce the symmetry transformation, we take this derivative operator, we act on the soft factor, and we convolute it against the function. And well, we find what we get. And so in particular, in the previous case, we saw that the SAW factor was a Green's function on the 2-sphere. But that was because we could associate the momentum of a massless particle canonically with a point on the 2-dimensional sphere, namely the direction in which it was propagating. But massive particles aren't canonically associated, the momentum of massive particles aren't canonically associated with points on the sphere, and that's easy to see if you consider the rest frame. In that case, there's no direction that's associated to that momentum. On the other hand, the momentum of massive particles do specify points on the 3-dimensional hyperboloid. And so in particular, what you find by acting with this derivative operator on the soft factor is you find a bulk to boundary propagator from a point in ADS3, which is associated to the massive momentum, to a point on the boundary, which is associated to the direction of the soft graviton. And so this is the transformation of massive particles under the supertranslational symmetry. Okay, so that concludes my review of of one of the examples of a precise relationship between symmetries and universal infrared phenomena. And so this was this equivalence between Weinberg's soft graviton theorem and a word identity for supertranslational symmetry. And so in particular, Weinberg's soft graviton theorem is usually thought of as a statement of universality of the infrared. And from that, and included in that is the following points. So that it's an exact relationship between scattering amplitudes, that the soft factor only depends on the momenta of the external particles and takes the same form for each particle and is independent of the precise theory. However, now that we have this symmetry interpretation also available, we can understand these properties as arising from symmetries. So in other words, the reason why there was an exact relationship between scattering amplitudes is because that's how symmetries behave in the context of the scattering problem. And the fact that the soft factor was the same, but depended only on the momenta of the external particles and had the same form for each particle, was because that was how single particles transformed under the supertranslational symmetry. And the fact that it was independent of the precise theory was because this is a property of it's a symmetry of theories of gravity. And so general theories of gravity will have this symmetry and therefore this behavior. Okay, and so that brings us to the next point, which is to consider to ask whether the universal structure of other infrared singularities in scattering amplitudes is also related to symmetry. And so in particular, one of the universal behaviors that we're going to be interested in is factorization. So what factorization is it's the statement that the gravitational S matrix defined with an infrared regulator factorizes into hard and soft factors, where the soft component is universal and contains all the infrared and collinear divergences. So in particular, if one considers a scattering process between only external hard particles, then what one finds is that this scattering amplitude for that process factorizes into two pieces, a hard part and a soft part, where the soft part is given by this formula here, and it depends on only the momenta of the external particles. And so in particular, it depends on an infrared, on epsilon, which is an infrared regulator in dimensional regularization. Eta is a parameter which is labeling whether the state is incoming or outgoing, and it's a sign. M is the mass of the external particles. And then the non-trivial dependence on the momentum can actually be entirely rewritten in terms of this parameter gamma, which is constructed from the inner product of two momenta. And you can think of it as the distance on the unit three-dimensional hyperboloid between points that are associated to massive or time-like momenta. So in particular, if pi is equal to pj, then gamma goes to 0. And so, like,
Is this a tree level formula? What is this formula?
no, this is actually, this resums an infinite class of diagrams. It's an exponential, so like.
But there are no loops here, are there?
There are loops. So this is resumming all, essentially, like if you have some scattering process. It's a summing a bunch of exchanges, soft exchanges, like all ladder soft exchanges.
But you don't let the, sorry, but you don't let the gravitons themselves go in a loop.
No, so this is that does not, well, okay, it depends on what you mean by gravitons themselves. The soft gravitons themselves don't go in loops. Like these external lines could have been gravitons.
I'm trying to understand how you're, which part of this is sensitive to the fact that that gravity is not UV complete as a field theory.
These are just infrared gravitons.
Yeah.
So that part is somehow in the hard part of the amplitude?
Yes.
I think what she's resumming into this soft factor is just a soft real emission and soft graviton in the loop. That's all.
Right.
Okay.
And actually in this formula, there's not even, we're going to generalize to soft real emission in a moment, but right now there's just the soft virtual exchanges.
So it's still infrared divergent.
It's infrared divergent, yes.
Mhm.
So, right. Epsilon is a parameter that's regulating infrared divergences. You take epsilon to 0, and this soft factor, this S soft goes to 0.
So the meaning of this factorization is that the thing with the hat on it is not infrared divergent?
Yes.
Or it is?
Yes. So you can take the infrared, right.
But is there an operator S hat that is not infrared divergent that appears in that formula, or is that just is this just a definition of the thing with the hat on it?
This is the definition of the thing with a hat in it.
Okay.
And I should say, you know, it's non-trivial because there's a formula here, right? That you can divide that all the infrared divergences can be captured by a simple formula, right? Because if you have something that's infrared divergent, you divide it by yourself, you always get something finite, and that's trivial. But then you have some simple form for what the infrared divergences look like. Okay, so yeah, so to reiterate, this is supposed to be a statement about, again, a statement of universality in the infrared. The idea being that the divergences are coming from soft virtual gravitons. So in particular, classes of diagrams like this, where the gravitons being exchanged between external legs are taken from the sort of soft part of the exchange. When the gravitons exchange between external legs are soft. And it's a statement about universality because there's some universal formula for these divergences. And again, similarly to before, it depends only on the momentum of the external particles. Uh-oh. Okay. So in order to, again, make a connection to symmetry, it will be helpful to instead consider the case when all the external particles are massless particles. And in that case, the formula for this infrared divergent part of the S matrix takes a slightly simpler form. So in particular, it's shown here. And just as before, we're going to do the same. Strategy will be to parameterize the momentum of these external particles by energies and points on the sphere. And so upon doing so, we find that this infrared-divergent factor can be written in this form. And so in particular, all the angular dependence is only through distance on the two-dimensional sphere between points that are associated to massless momenta. So since this angular dependence is entirely in terms of these pairwise distances on the sphere, we can express this angular contribution as a two-point correlation function on the sphere. And now we can exploit the fact that this is the exponential of some pairwise structure and express the infrared divergent part of the S matrix entirely as a correlator of a free field, which I'm calling C. And so the contribution from each external particle is some vertex operator V, which is an exponential of C. And the utility of doing that is now we can express factorization. Instead of being a statement about scattering amplitudes, we can talk about it as a statement about asymptotic states. So in particular, we can regard it as the factorization of single particle states into an exponential of this operator C and whatever is needed to reproduce the hard part of the S matrix. And so what I'd like to now explain is what the meaning of this decomposition is. So suppose this field C transforms by a shift F. Well, then the vertex operator, which was reproducing the soft part of the S matrix, transforms according to this rule. But this was the net infinitesimal transformation of single particle states under supertranslations. And note that the transformation of a field C by some shift can be interpreted as the transformation of a Goldstone boson under supertranslation symmetry. So what this means is that this decomposition can be interpreted as the decomposition according to the supertranslation symmetry. So in particular, the part that is reproducing the soft part of the S matrix is the part that is charged under supertranslations, and the part that is reproducing the hard part of the S matrix is the part that's neutral. And moreover, we saw that the soft part of the S matrix could be calculated as a correlation function of this field C, and now we see that C can be interpreted as the Goldstone boson associated to supertranslation symmetry.
Can I ask a quick question?
Yes.
Just to make sure I'm following. So you had some 2-point function for C. That 2-point function, if you take derivatives of that, like that d sub x that you had before, is it a delta function on the sphere?
Yeah.
Oh, okay. Thank you.
Okay, so now that we have this symmetry interpretation of factorization, and we applied it in particular to the case when the external particles were taken to be massless, well, since we know the transformation, the generalization of the transformation of single particles under supertranslations to massive particles, and it better be the case that the story that we just told generalizes appropriately. And so in particular, we previously argued that the factorization should be thought of as the decomposition of single particle states into a neutral piece and a charged piece, where the charged piece was a function of the Goldstone boson and fully reproduce the symmetry transformation of the single particle state. So thus we should be able to deduce by symmetry what the appropriate vertex operator associated to massive particles should be. So in particular, we can compare recall the transformation of single particle states. So in the massless case, we found that it was this local function of f, whereas in the massive case, we had to convolute it against this bulk to boundary propagator from a point associated to the massive time-like momentum to the boundary, which is a sphere. Now, the Goldstone boson, its transformation is simply fixed symmetry, so it's the same in both cases. And in the massless case, we saw that the vertex operator, which fully reproduced the transformation of a single particle state, took this form. And so note the relation of this vertex operator to this transformation is it's simply that you multiply by I and you exponentiate this and you replace f with c. So let's do the same thing for massive particles. Namely, let's multiply this by I, exponentiate it, and replace f by c. So this would be our guess for the appropriate vertex operator. And indeed, under the symmetry transformation of this Goldstone C implies that the symmetry transformation of this vertex operator is precisely that of a single particle massive state. But the final check is that if I take a correlation function of such vertex operators, that I fully actually reproduce the intricate formula for the infrared divergent part of the S matrix in the presence of massive external particles. And so indeed, one can show that using these vertex operators for massive particles and the 2-point function for the Goldstone boson, that you can fully reproduce this complicated structure.
Can I ask one question here? Yes. So if I understood it correctly, if I take some one particle state, which is an irreducible representation of Poincare group, you can recast that state in terms of representation of BMS or asymptotic symmetries in a way that there's a Goldstone mode under that BMS symmetry and there is a neutral radial mode. And so for each one particle state, according to the Poincare state, can be decomposed into Goldstone mode by the BMS symmetry and radial. Am I getting this picture correctly?
Yes, I hadn't quite thought about it in that way, but yes, that's the statement, yeah.
Okay, then in order to get IR safe observable, I just strip out the Goldstone mode part and only focus on the hard neutral part. Is that? I mean,
yeah, so I'm not actually going to talk about that today, but yes, so it's known that one way that you can construct infrared safe scattering amplitudes is to dress them with Faddeev-Coolidge dressings. And you can actually show that a certain class of a generalization of a certain class of Faddeev-Coolidge dressings are precisely these exponentials of the vertex operators. And so indeed, well, up to a sign. And so indeed, dressing these states is equivalent to stripping off. Yeah.
Okay, awesome, thanks.
There's something about the this presentation in terms of a Goldstone boson that I'm not entirely following. Maybe you could clarify. For the massless case, is the Green's function for the C field supposed to be a standard Green's function for a massless particle on the sphere?
No.
What is the Green's function?
So I had written it previously, but I think it's easier. If you're working in stereographic coordinates, then this thing is like
what action would produce that? I'm just confused because the claim that you made a very strong claim that it's a Goldstone boson by saying that it's in the action principle or whatever formulation you have in mind would be invariant under shifting C by any function, right? Because the shift in C is just any function.
Yes.
If I understood correctly, right? So whatever dynamical principle you have, it should be that the action function will be invariant under shifting C by any function, which sounds kind of implausible. So I'm trying to understand how to reconcile that.
Well, let's see.
you know, like a free field has a lot of symmetry, but the action is not invariant under shifting the field by any function.
That's correct. I think, right. Let me.
Sorry, wasn't F the same F appeared in the different representation of the charges? Like you convoluted it. So basically, the infinite amount of F captures infinite dimensional symmetry that you're talking about, and that therefore it amounts to saying that this is shift under all of those infinite amount of generators. Wasn't that the same? Or probably I was.
I'm with you, Sungwoo. I'm saying the same thing, but I'm going a little farther, which is saying that it sounds a little weird to say that there can then be a field C whose dynamics, a local field C whose dynamics is invariant under shifting it by any function. I'm trying to understand what that field would look like.
Okay, so let me say this. If you're at the level of right. So the supertranslations, which I didn't describe, the part that I didn't describe is that they're part of the diffeomorphism group. And so in particular, this C is directly related to a component of the metric that you can show is pure gauge. So it's shifting by C is shifting C by a function can be shifting C by a function is implemented by doing a supertranslation, which is a diffeomorphism, and it is a symmetry of the Lagrangian.
Okay, at the 4D level, I agree with that, but I think right now you're trying to mix in some 2D intuition. You're trying to say, well, we can think of C as some field on the sphere at null infinity, and this field C has some very simple 2-point function, and then we can exponentiate it and make vertex operators and do Wick contractions and so forth, and then get soft factors. And I'm trying to take that seriously, and then I'm trying to interpret what are the independent dynamics for the field C as described on that sphere. And I'm having trouble thinking what is the action principle defining the field C such that it could be invariant under shifting C by any function. And that might just be my lack of creativity, but I wonder if you have an idea what the action principle for C is as formulated on the sphere, not as formulated in 4 dimensions.
I mean, okay, so I can tell you, you can have a
well, just how do you get this propagator for C? How do you get CC as Z squared log Z?
well, so this followed, I mean, that was fixed by having it reproduce the soft part of the essay.
Yeah, but how would you get it on the sphere? What theory for C on a sphere would produce that?
What theory? Well, you know.
Maybe we can talk about it after if it's delaying everything. I'm just trying to understand what the dynamics is for C.
Yeah, okay. Okay, so yeah, let's talk about it afterwards. But okay, so just to summarize what we've found so far, we've found that the factorization of the S matrix into an infrared-divergent soft part and an infrared-finite hard part could be interpreted or is equivalent to the factorization of states into symmetry charged and symmetry neutral components, where the soft part is fully reproduced by a correlation function of Goldstone bosons that are associated to supertranslation symmetry. And so the final part is to generalize this story to amplitudes that include external soft gravitons in the asymptotic state as well. So we already know that the amplitudes that have external soft gravitons are governed by Weinberg's soft graviton theorem. And so I've rewritten that here. And now if we want to study factorization, well, if we look at the right-hand side, this scattering matrix element has no external soft graviton, so we can just straightforwardly apply what we already learned about factorization in the last part. And so in particular, as I've already mentioned, the soft part is capturing all the virtual infrared divergences. And on the left-hand side, now factorization generalizes to include the soft graviton in the infrared divergent part. And so, in other words, the soft part of the S matrix is now capturing both real and virtual infrared divergences. And the reason why this soft graviton, or so as written, isn't actually infrared divergent is simply because it does produce a pole in energy, but we've written in such a way such that we're just picking out the residue of that pole. And so again, to sort of emphasize or the 2D structure, we're going to introduce this other operator in, which is constructed from soft gravitons. And so in particular, this means that the hard part on both sides of the soft graviton theorem is the same and it cancels. And so the soft graviton theorem, upon applying factorization, takes this form. And schematically, you can recognize that now this soft graviton is playing the role of a two-dimensional current that generates the symmetry. So this is, roughly speaking, the form of a ward identity for correlation functions, where n is the generator of the symmetry. And therefore, if we want to capture the soft, or if we want to reproduce the soft part of the S matrix in the presence of external soft gravitons, then it should be represented by a correlation function of Goldstone bosons and the symmetry generators N. And so what we now needed to do is, since we're now these involve also the symmetry generator, and we need to specify the correlation functions of N and C. And so in particular, because Weinberg's soft graviton theorem tells us that the soft part of these different S matrix elements must obey this relation, there must be a non-vanishing correlation between the symmetry generator and the Goldstone boson. And indeed, a two-point function of this form will reproduce this formula. And this you could also understand as arising from a symplectic pairing between a symmetry generator and a Goldstone boson. And the final thing to ask is whether there need be any correlations between multiple symmetry generators or soft gravitons. And to deduce that, one studies Weinberg's soft graviton theorem, but generalized to multiple soft emissions. And in particular, what one finds if you have two soft emissions is that the ultimate soft factor that you find is just the product of two of the soft factors, where these only receive contributions from the other particles participating in the scattering process. And roughly the way to understand that was, if you recall, these soft factors could be interpreted as the eigenvalues of single particle states under a hard charge, which was proportional to the energy. And so there is no contribution between these two, simply because these are zero energy gravitons and therefore carry vanishing hard charge or have a vanishing soft factor. And since this net soft factor is just two copies of the single insertion, there's no correlation between the n pluses. And so their two-point function, for example, vanishes. Okay, so now that we found that the soft part of the S matrix can be reproduced by a correlation function of generators and Goldstone bosons, and we've specified the correlation functions that are needed to reproduce the soft part of the S matrix. Let's use the soft part of the S matrix to construct an observable that's protected by symmetry. So a natural infrared safe quantity that one can construct is the ratio of these two soft parts of the S matrix. And so the reason why this is infrared safe is that in defining this N plus, we multiplied by a factor of omega, so we were picking out the residue of the pole, so there is no, so it removes this singularity, or in other words, picks out the residue. And otherwise, there were virtual divergences that were captured by the correlation function of these vertex operators, but they cancel in the ratio. And of course, if we use Weinberg's soft graviton theorem, then we know that this is equal to the soft factor, which is obviously an infrared safe quantity. But what is the interpretation of this ratio? We'd like to say that it's a nice observable that's protected by symmetry. Well, if we multiply and divide this ratio by the hard part of the S matrix, we can then interpret it in terms of ordinary S matrices, and we see it's the ratio of these two S matrix elements, which we can think of as then telling us, which we then can interpret as being telling us the expectation value of this operator in some scattering process. Okay, so that's one meaning of this observable, but of course, to really understand what that means, we need to know what this N plus is. So what we had written for it before was we had written it in terms of these creation and annihilation operators of zero frequency gravitons. And we could, of course, rewrite it in terms of a field, and it's telling us something about the zero frequency component of the time derivative of the radiative gravitational field. And so we want to interpret this as a nice observable, and said this way, the zero frequency limit of the radiative gravitational field doesn't really sound like it's observable. But that's just poor phrasing. And so the key thing to notice is that if you take omega to zero, this is a total time derivative. And so really this N plus is to be identified as with a permanent shift in the asymptotic metric. So in other words, the ratio of these soft parts of the S matrix are telling us about the expectation value for a permanent shift in the metric in the background of a scattering process. And that is much better, because that is something that people have known is something that is observable. And so in particular here, I've shown on the right a clip from a paper from 1987 by Brzezinski and Thorne, in which you can see they have a formula for this permanent shift in the asymptotic metric. And they've in fact directly related it to something which we now recognize as Weinberg's soft factor. And so back in 1974, Zeldovich and Polnareff explained how one measures this permanent shift. And that's through something called gravitational memory. So the idea is that if you have a pair of inertial, is that it can be observed by a pair of inertial detectors. So if you take these inertial detectors and you send them through a burst of radiation, well, before they pass through the radiation, their world lines will be at fixed distance from one another. As they pass through the radiation, it will cause their world lines to oscillate. And then after they've passed through the radiation, they will again be at fixed displacement they will be at fixed distance from one another, but that distance need not be the same distance that they were displaced originally. And in particular, the change in the relative distance between inertial observers is precisely capturing this change, measuring this change in the asymptotic metric. So mathematically, this can be understood through the geodesic deviation equation. So in particular, the geodesic deviation equation directly relates the relative displacement induced by the permanent shift in the metric to the relative displacement. Relate the permanent displacement between inertial observers to the permanent shift in the asymptotic metric. And so This is how one measures the net shift in this asymptotic metric, and it answers the question of how you're supposed to measure this zero frequency component of the soft radiation. That is, you tile the celestial sphere with inertial observers and measure the change in their relative displacement. Okay, so our goal today was to understand several instances of a precise relationship between symmetries and universal infrared phenomena in the context of gravitational scattering amplitudes. So I began with a review of the equivalence between Weinberg's soft graviton theorem and a word identity for supertranslation symmetry. And this has suggested that actually, perhaps more generally, the universal structure of infrared singularities and scattering amplitudes might be related to symmetry. And so in the second part, we saw how the factorization of amplitudes into infrared-divergent and finite components is in fact equivalent to the factorization of states into supertranslation charged and neutral components. And we saw that in particular, the supertranslation, the soft part of the S matrix was reproduced by the part of the states that was charged under the supertranslations. And we used that to construct an infrared safe observable, which we saw then could be identified as gravitational memory, which is something that can be measured. And so, so sort of the outlook and future directions is that actually this 2D language does have a little bit more structure. So in particular, one can study if there's a natural way to identify scattering amplitudes in 4 dimensions with correlation functions in 2 dimensions. And in this case, the global Lorentz symmetry in 4 dimensions translates into a global conformal symmetry in 2 dimensions. And so one might then want to interpret this 2-dimensional theory as a holographic dual of scattering 4-dimensional spacetimes. And in this case, these operators, the generator of the symmetry and the Goldstone boson, are operators in that holographic dual. And finally, the equivalence between soft theorems and word identities for infinite dimensional symmetries has many generalizations to a wide variety of contexts, including subleading soft theorems, gauge theory, supersymmetric contexts, and many more. And so there should be, but it has not been widely studied, analogs of these generators and Goldstone bosons that govern the physics of these different cases. So thank you, and we can take questions.
Thank you very much. That was a great talk. Wanted to ask if there are any quick questions, perhaps before we have a longer discussion after a quick coffee and bathroom break.